Hello and welcome to this session on theory and application for shells that is used in analysis and design of structural systems. And it is a very long and interesting subject as such. And to start in a new year, so I wish Happy New Year and Happy Diwali to all. This topic, which is very elaborate, very distinct, and it is actually plates and shells have been researched in the last 20 years, and its applications has various applications in different forms of the structures that we are coming across every day. So, what theory to use and what are the assumptions for it are very crucial, and this is the subject of interest shown in the WhatsApp group also that design of flow slabs, that is the flow systems, whether you design it in tabs or especially in safe, it is now titled as structural design of flow systems, and that also will work in the similar manner. Same, we go for the foundations, bridge decks, uh, uh, fabric structure. So different applications are there, and uh, where to use what, that is very important. So when we are going into finite element analysis, this is very crucial. Whether we are choosing a membrane, whether we are choosing a plate, whether we are choosing a shell. In shell also, two different types are there. So that is what we are going to discuss today. The aim is to understand, means go deeper. However, one or two sessions would not help you to or me to deliver or understand the subject in depth. But how much is useful to us and whatever we are doing in practice, what relevance it has, that much I can cover. And I can give you a few sources from where you can get deeper understanding. And if required, a separate course may be there. But there are already NPTEL courses on plates and shells, and especially by Professor Kant of IIT Bombay. So he has been instrumental in this subject, and he has also done his contribution in this domain of work and recognized from India. So Professor Kant from IIT Bombay, his NPTEL videos or sessions are there. So I would request all to go through it step by step because it is a mathematical formulation. It goes into the Taylor series and the basic fundamentals
Sir,
that
please
behind
explain, please tell his name once again, sir.
whose name.
Sir, that lecturer name IIT Bombay.
Yeah, I'll show you on YouTube. You can take a screenshot of it.
Okay, sir.
We will go through all these parts because uh, for me to cover in two lectures or one lecture, it is very difficult because maybe this some part has will be taken by IIT Roorkee in the coming sessions as a course rather than a webinar. So what I will cover today is let us rediscover what we are doing in practical field and connect with the theory basically. And what are the sources and what you should be doing to go deeper into it. And what applications are what you are using, you should know what you are doing. What parameters are there in the software that you have to input that we will see like M11, M12, M22. So what are those parameters referring to and where to put what and where to put not. So that is very critical. So before starting the session, the I will it is being recorded as well. So the recording will be shared in maybe 3 days from today or today, depending upon that time schedule. So I'll upload it and share with you all. So many people are not able to take it live, so they will take it recorded session. And with the starting point, I would like to know that what is your exposure in finite element analysis, and what is your exposure in understanding of plates and shells. So one by one, if you can just give something, what is your level of understanding, so I can pick up from where you already know. Okay. So anybody would like to share their exposure on?
Good evening, sir.
Yeah, yeah.
Sir, my name is Shahid Rabbani. Actually, sir, my question is that while we designing the slabs with IS code, there are certain provisions given in the IS code that how do we find the moments and whatever given in the IS code. But if we deal about the theory of plates and shells, so there is a different approach of getting all those type of things, finding exactly or whatever is there. So, in practical scenarios, uh, which approach should be followed in designing of the plates or plates actually slab with IS code or with the what the approach we will learn in the theory of plates and shells. And apart from that, how we I also want to sir learn here from you that how we will connect what we learn in theory of plates and shells in the design criteria.
Okay. Noted, Shahid. Now the
Yes,
my question was that what is your exposure or your understanding of FEA, that is finite element analysis,
yes,
and the software that you are using, and plates and shells. Basically, what is your background to it?
yes.
So,
Actually, regarding the plates and shells, I went through the syllabus and I know something about that. I want to know sir the practical applications of that thing. Yes,
okay, we will go through that. That is why we have kept this session. Only thing is, what do you know about plate and shell? You can, what is your understanding of plates and shell?
like sir in plates and especially in the plates we find the deflection, how much deflection it is coming under the different types of loading. And we also find that the what are the maximum moments that can occur in the plates especially. uh, so and this is the thing sir, that I know about the plates especially. I'm not very clear about the shells right now.
Sir, plates are rectangular or square elements. Shells are conicals.
Okay,
No,
And
shells are the curvily. These plates are there, but with a very small. One dimension is very small with compared to other two. But the plates are the difference between plates and shells are that in shells uh, there is a curve. It is in curve like the thickness is embedded between the two curved lines.
okay, fine. So, any other would like to add to it?
sir, plates are designed for bending moments. Shells are designed for hoop stresses.
Okay. So, any other input on that? Okay. So, Rahul, are you able to connect with us with audio? I am not able to hear you. Need to check your mic. So still not audible.
Hello.
Yeah, yeah. No, you are audible.
Okay.
Yeah, you would like to add something on plates and shells?
No, sir. Actually, I'm new to this, so that's why a little bit I know something. The normally is that we in what IS code prescribes that is based on yield right theory, and what we are doing right now will be in FEM base.
Okay, so you are working as structural engineer.
Yes, civil and structural engineer. Yes, sir.
Okay, so how much experience you have in?
2 years. Right now, I'm in actually doing solar power plant design.
Okay, thank you. So Mohammed, are you there? Hello. Okay. Someone's mic is on. Hello. Someone's mic is on. Can you switch off the mic? Okay, thank you. So more or less, you have given a basic fundamental difference in plate and shell. Hello. Can please check your mic? I'm not able to see anybody's mic on, but still the volume is coming.
शम स्प्लेंडर बाहर यार प्लीज.
Hello. Can you off the mic? So can anybody see any participant whose mic is on? Or else I'll have to switch off the mic of all participants. Okay, Sayed, can you speak? Are you able to get the option to speak?
Yes, sir.
Okay, okay, fine. So we'll continue ahead.
Sir, currently network problem. Okay, sir.
Sorry. Yeah. Okay, so all means you have hit the means right note on plates and shells. So let me be more specific into it, and we'll see the applications of that. So I'll just share my screen. If not visible, then let me know. So is my screen visible to you? Hello, is my screen visible to all?
Yes, sir.
Okay. So starting with the first description, that is the plates. Now plates have, or I would say, let me start with FEA, what we do directly to that so we can relate better. So it is FEA analysis, finite element analysis that we are doing. Now it has three type of definitions that you will give into this. First is a membrane, second is plate, and third is the shell. Okay. So each have their own distinct characteristic. Okay. So what is membrane and related to? So what type of forces will come in the membrane element? So membrane element take axial forces. Okay. And it does not take bending. So no bending. That is no out of plane stiffness. Okay. So what will happen if there is no out of plane stiffness? 100% force transfer to the supporting elements. So it in its itself out of plane bending, it will not take part, and it will only take the axial force like a cord. Okay, and it will transfer the bending to the supporting elements. So that is the characteristic of a membrane. So when in what type of structures do you find membrane action? If we try to enlist this, number one is the fabric. It has
Staircases,
no,
staircases.
yeah, yeah. So second example would be staircases. Okay. Then there will be ramps, and there will be very thin slab, which has very negligible out of plane stiffness. Then you will take it as a thin slab. So all these examples of a membrane element. So whenever you come across that what to define membrane or a plate or a shell, you have to keep this in mind that there is no out of plane bending stiffness for the membrane elements. Now this is what is considered in our IS 456,000. So whatever we are using the factors or parameters in the table that is given, that is two side continuous, one side is continuous, or all those parameters are given. Okay, so in this, the consideration is the slab is a membrane element. It takes only the axial forces and transfers the out of plane uh, forces to the supporting elements, that is the beams. Okay, so this is what is the way when we are doing the manual analysis and design using IS 456-2000, you will get uh, using the membrane action. Okay. Now, when we go to the plate element is basically representing what? Bending and twisting. So twisting action, bending action, both the plate element is able to take, but it does not have no in plane. Stiffness is accounted. And what you can say, shear is not accounted. Okay. Now, what type of elements the plate you can model? Okay, one is the floor plates. Those are there that have very less thickness as compared to their other size. Okay, so then you can model it as a plate element where there is no shear governing action, only bending is going to be there. Now, what else can be modeled as a plate element? Any example that you have? Any model as plate, which has mostly twisting and bending?
Sir, surface of the ship, or we can say the aircraft, the outer layer of the aircraft can be defined as the plates.
Yeah, aircrafts are there, then shells are there. So all these types can be modeled as the plate element, which has very thin, very low thickness. Okay, so shear will not
Yes.
dominate. Mostly the flexure action will dominate. So in all those cases, it is taken as the plate element. And the out of plane bending is considered for the analysis or the design. Okay, so that would be the example of the plate element. Now, when we come to the shell, now it is a tensor quantity. Okay, so it is a second order tensor, and it is a combination of membrane plus plate. So what it accounts for is the bending moment, twisting moment, and shear. So all three parameters are considered in this shell element. Now in that there is a twist. Now how much here to consider? So now there will be thin shell and there will be thick shell. So when do we consider the thin shell? When deformation, basically out of plane deformation. Okay, out of plane deformation is less than thickness of the element or the plate. Then you can call it as a thin shell. So whatever the deformation happened, it is lesser than or equal to the thickness of that element. Then you can say it is a thin shell element, which is uh, what we say uh, in linear range. Now, again, if the deformation is higher than the thickness, then it becomes geometric non-linearity. Okay. So this is a thin shell element with small deformation. This would be the small deformation. This would be the large deformation. So thin shells, which deformation is greater than the thickness out of plane, will come under large deformation, which will be having geometric non-linearity, and small deformations, which will be linear element, and we can what we say that shear consideration will be less. So geometrically, it will become non-linear in the thin shells also. Now thick shell. So when the thickness of the element is greater than 1 by 10 of the length of element, then it becomes a thick shell. So let me take 1 by 10. So if I take 1 meter length and 10 of it, so it becomes 100 mm. So thickness of the slab is 100 mm and the length of the slab is 1 meter only. And your thickness of the slab is going to be 110 or something like that. Then it will become a thick shell. Now, if it becomes, let's say 10 meters, then this will become 1000. Okay. So your T is what? Let's say 110, not more than that. Then this will become a thin shell. Otherwise, it would become a thick shell. So thin shell versus thick shell, that criteria, uh, uh, what classification we say. So that classification is in this particular format whenever you are doing the analysis in, let's say, Abacus, or you are doing in ANSYS or SAP 2000 or ETABS or SAFE. These are all the CSI products that are FEM based. CAD is your stiffness based. So in that, mostly you will do the plate modeling. So plate modeling, so what can happen is plate can also be identified as thin shell. Okay. So you are modeling thin shell as a plate in the STAD software, in which the bending is higher. However, shell element has a characteristic that it also has shear. So like if we do the higher thickness, like the thickness of the floor is 500 mm or 400 mm, and your length is 3000. So 3000 divided by 10 is only 300, and you have given a slab thickness of 450. Then it will become a thick shell. Now, if it becomes like 4000 or 5000, okay, so 5000 it will be 500. Then you can classify either in the analysis, because as the thickness will increase, shear will start dominating. So when shear will start dominating, you will assign it as a shell element, not as a plate element, because plate element will give you only out of plane bending, not the along the thickness, whatever the shear is going to develop along the thickness of the element, it will not be able to, you will not be able to discover that. So I think this much is explanation is basic explanation is clear to you, as I tried to simplify it from whatever I have referred it. So what are the examples? RCC floors, then it is bridge decks, then foundations, and flat slab. So all these are examples of shell. Okay, so these were examples of the plate. So these were examples of the plate. These were examples of the membrane, and these are the examples of the shell element. So either it is a thin shell or whether it is a thick shell. You have to identify that, and our IS 456-2000 is uh, considered, the parameters are considered based on the membrane theory. Can we go further? Hello. Okay. So now there is a theory of elasticity which has to be understood, which was basically taught to us in our undergraduate course. In this, now there is a element of size 3D element, dx, dy, and dz. This is the element which will be having dx length, dy length, and dz as the thickness. Now this is the XYZ coordinate system. This will be X, this will be Y, this will be Z. See, somebody is trying to join. Okay, so this is the coordinate system XYZ, and now this is the coordinate system. Now Cartesian coordinate system, we are going to use it. I'll try to draw the third dimension. So now it has the six surfaces. So this will be sigma X, this is sigma Y, and this would be sigma Z. Now what are these stresses called? Can anybody tell?
Principal stresses.
Yeah, so these are the principal stresses along the X, Y, and Z direction. So I have shown for three surfaces. Same you can assume for the other three sides, in which when the differential equation is formed, okay, so there will be some sigma X plus delta sigma, right? Some delta increase will be on the other side. So this will be sigma X, delta increase on the other side. So positive side and negative side, the forces will get generated. Generally, we take tensile forces as positive in our metric system whenever we are doing with the structure. So tensile forces are to be taken as positive. So when this 3D object is there, okay, so this is a 3D element having what we say that size dx, dy, dz. So this is the volume of the object, small object we have taken from the any, let's say, flow system that we are going to evaluate. So we want to convert this general theory into our specific plate element. So before that, we want to model the plate element, that what is the basically plate saying. So plate is basically any object which is between two surfaces. Okay, so like this, and So someone has just joined. Can you tell me your name? Hello. Hello. Can you type in your name? Okay. We'll continue. So what is a plate element? Basically, this is the surface one, top surface, and there will be bottom surface, that is surface two. So plate is an object which is between two surfaces and having thickness T. And this is your midline. So this is a plate element. Plate element is between the two surfaces, top and bottom, and which is having a thickness T. So you can see the difference between the two objects that I have drawn, which is a 3D element. We have converted it into a 2D element, and that 2D element is a plate. Okay. So 3D element we have converted into 2D element called the plate. And what will be the difference now? So that let me just draw the forces here, tangential forces in this 3D element. So here it will be x. Here also it will be x. So this is the normal direction. In which direction the force is getting acted, you have to write it in the second subscript. So vertical is z, horizontal is y. This will be tau y, again tau y. Here it will be x, and it will be z. Right. So tangential stresses are getting generated, and these tangential stresses we are neglecting if we are using a plate element. And in thin shells also, uh, plate theory is valid, but at the edges and also at locations of cutouts. Okay, plate theory does not work. So modeling thin uh, shells as plate element, you need to check in the software or in the analysis using the differential equations that how it is giving you the results. Okay. So I am talking about the plate, not membrane. So membrane and shells are different. Plate can be used as a thin shell. Okay. And this is what we are deriving. The plate is a 2D element which we are deriving the equations for. So what is the basically what is that we are doing? We are having a 6 by 6 matrix in which it is sigma x, sigma y, and sigma z. This will be tau x y, tau x z, tau y x, tau y z, tau z x, tau z y. So this nomenclature should be clear to you in which direction the forces that are getting added and how you will generate this matrix 6 by 6 matrix which is representing this 3D element which is having the size dx, dy and dz. Diagonally, the matrix is symmetrical. That means tau xy equal to tau yx, tau xz equal to tau zx, tau uh, yz equal to tau zy. So this is the symmetry in the matrix that exists, and this is a second order tensor matrix for the stresses. Okay, so we have derived the stresses in this. So what are the things to be derived? One is the stress, then would be the strain, and you have to check the strain compatibility. So all these checks you have to do when you are evaluating any three-dimensional object. And same you have to repeat for this type of structure. So you need to refer a good textbook in which the this formulations have been given, and you can refer the lectures of Dr. Khan that I will show you. So now we are converting this into 2D element in which only sigma x and sigma y is there. So tau x y, tau y x. So this is your 2 by 2 matrix that you will derive. In this also tau xy equal to tau yx. So the symmetric about the diagonal. So this is what is we are actually doing when we are using the plate element, and really a body is a 3D element, and what helps us using the 2D element. So what has happened is that when there were no computers, there were approximations and assumptions that were done by the people who derived it. So what you should refer is the Love's theory. So he was a mathematician. So let me write the full description of it that you should refer if you want to create a you know deeper background into this theory. Let me open that document. So this was the theory based on which all other theories got derived. So this is the mathematical theory of elasticity, was in 1927. Then what had developed was by now that was another significant I will write is Timoshenko. So Timoshenko and Krieger, theory of plates and shells, they have written a textbook on that, which is quite difficult to refer. So if you don't have good mathematical background, you will not be able to understand this textbook. So first have get a good mathematical background to use this book. Then there is very important Poiter. So what he did was theory of inelastic shells. So this is what we are interested more because our labs are the thin shells, not the thick shells in general. Wherever the thick shells will come, we have to take it. Inelastic shells. This was in 1960. Now, other was Kirchhoff. This is also very fundamental theory that developed the uh, theory for the plates and shells in different forms. So, boundary conditions and edge effects. So, our analysis is always in the boundary conditions, and whatever at the edges are generated, that needs to be evaluated. That was in 1950. And one more important, Resiner, and his contribution was not many, so I would not write any specific because his theories are yet very read and being understood and developed further. So you can refer his work. Okay, so now in this one more to be added is of the uh, Dr. Khan. So you can also write Dr. Khan. So he has given his contribution, IIT Bombay. So all these people developed the shear deformation theory. So if you refer any subject on shear deformation theories, so anybody is aware of shear deformation theories of any type? Anybody has come across or heard? Anyone? So shear deformation theories are used. These are used to model the behavior of plate structures and composite material like we do in the bridges or in the PEP buildings by considering effects of shear deformation. In cases where you cannot avoid shear deformation, you are using the shear deformation theories, and your search word in Google should be shear deformation theories. So that will help you to take it to a higher level because there are uh, first order shear deformation theory, second order, third, fourth, and fifth. So most of the research that you will see on the fourth order, what I have come across that few people have developed for the fifth order as well, but its application is not yet understood clearly. But up to fifth order, the shear deformation theory has got developed. So then there is a Mendelian theory. Okay. You need to see what software you are using and what theory is being applied. So Mendelian theory is there. This is one of the theories. So first order shear deformation theory, also known as the Mendelian Resiner. what Nema had written last slide. That is very critical. So Mendelian-Resiner theory is your first order theory. Mostly we are living in the first order theory right now, in which the H by L ratio is of the order of 1. Okay, how the uh, now the shear deformations become more critical. The transfer forces from the composite action becomes critical as the depth of the slab. Okay, this is the depth of the slab. How the variation is happening in the depth of the slab, the forces. This theory of the higher order will become critical. Where there is variation along the depth or some complexity, your shear deformation theory of particular order you have to apply. For that, you need to have understanding of that particular theory. Okay, so when I'm saying that Mendelian-Resiner theory, you have to go through it and understand what is actually what they are meaning by Mendelian-Resiner theory. So out of plane displacement is independent of Z coordinate. So in this, what this theory basically says that out of plane displacement is independent of Z coordinate. So there is no dependency on Z coordinate and you are dealing in XYZ coordinates only. Okay, so this is the basic what we are also dealing in our thin shells in the slabs. So in-plane displacements are linear functions of thickness coordinate. So one is out of plane, one is in plane. In-plane displacements are linear function of thickness. Material linear elastic, perfect bonding between fiber and the matrix. So it is a perfectly bonded element. Okay, then we are able to use it. If it is a composite slab, then it is not a perfectly bonded element. So in that, we may not be able to use a Mendelian-Resiner theory. I hope in two simple sentences, I'm able to give some hint to you that what is the theory actually going to be used for. Now, higher order shear deformation theory, we will now go after first order, all are higher order. So this theory relaxes the assumption that straight fibers remain straight during deformation. So, so before and after bending, there is a change. It does not remain the same. So fibers not remain the same after bending. So this is a common assumption for all higher order shear deformation theories. So I will leave it up to this right now because I will not go in the uh, more of these higher orders because mathematical background and your what we say the differential equations are needed to understand in more depth for the displacement. You need to develop the equations for strain and the stress. You need to derive the equation. So all this will be covered under Dr. Kant or one NPTEL other courses there that I will show you, and also the textbook or the any other references that you will come across. You can refer that. But if you search for higher order shear deformation theory, you will get it lot many literatures. So for composite action, you have to go for higher order shear deformation theory. You cannot go for the Mendelian-Resiner. I hope that is clear that what we are actually dealing in our RCC slab is a Mendelian-Resiner theory of first order that we are actually looking into that domain. And for the bridge deck, you have to go for the higher order shear deformation theories. So there is another thing called when we had seen the small plate like before, the small plate element I have taken, and when I take a shell, so as you had told that shell is having a curvature, that means it is not a straight element. Okay, so how FEA analysis is able to use this thing, because if I am modeling any large curvature element, then we are taking a very small micro elements like this, dividing the structure into finite elements. Okay. Why we are doing that? Because we are not able to handle this entire geometry with the given mathematics that we have or the computer system that we have. Okay, so what we are doing is we are giving the mathematical approximations that we had done into small elements. Whatever the mathematical approximations that we had assumed apply to these small elements which are nearly straight, not straight, but they are nearly straight. So our mathematical assumptions to be true, which are mostly true in the 2D element, we have to check for the 3D element that to derive the stresses and strain, and that should meet your derivation or the assumptions or the software results. You can check that with your basic mathematical derivations. So that is what many people do. They derive it, they model it, they code it in the software, they derive the stresses, strain, displacement, then they check the software whether it is able to give the same result or not. Okay. So this use in FEA and use of FEA is having the small elements which are nearly straight, and the mathematical approximations can be applied to it, and we can derive the results. Otherwise, we will not be able to derive any result. So this is the basic difference between shell and plate. Plate is a straight element. So now, what type of quadrilateral or triangular? Two type of meshing, that is what you decide. And the plate element is a 2D element that I had shown, sigma x, sigma y, two directions only we are considering the stresses. Okay, so now the time is to derive. So for this, if we remember sigma x, what we had taken was for this principal stress, and there is a normal stress. So this is the x, this is the, let's say, y, and this is the z that we had taken previously. So if I draw it over a plan, so previously everything was like this. Now I am having a different plane on which I need to find the forces, which is at an angle of theta. So right now it was x and y like this. Now it is having x dash and y dash. So these are called the normal stresses. These are not in the principal direction. So we need to derive normal stresses. So what we derive is sigma x into cos square theta plus sigma y into sine square theta. I think this we have derived it. Any book of H.J. Shah or solid mechanics, if you use, again, you can go through the derivation. Uh, Plus 2 tau xy. From Mohr circle, you can derive it. Sine theta and cos theta. Right. So you had seen that there is a Mohr circle in which, like this, angle of theta here, right? So this is your sigma x, this is minimum sigma y. So this is the, so from that you derive the stress for this particular point, okay, which is at an angle theta. So based on that, all these derivations are there using the Mohr circle. So they all apply here for the derivation purpose, and you should be thorough with the first 10 fundamental principles before using it for your particular purpose. So sigma y, and on this, if we see the sigma y, so what will be sigma y? It will be sigma x plus sigma y plus again, so this will become sine square theta, this will become cos square theta, and this will be your minus 2 tau xy sine theta and cos theta. Tau xy will be minus sigma x minus sigma y, okay, sine theta cos theta plus tau xy cos square theta minus. So I hope you remember this theory that was taught previously. So this is what we have derived for the plate element, which is a plane theory. So I would like to take your, are you clear with what I have shown? Because this theory can go long. It will take 1 month complete, complete understanding of the background that we are going towards. So if you are clear with basic understanding, I can move to the software. Otherwise, we can go more into the shells, like plate and shell, then it will become a different classroom session like that. So what is that you want me to do next? So based on your current understanding, you can tell me that whether I should take up with the software and go ahead, or and the given understanding is okay with you, or you need to have higher understanding on
Right. You can move to the software.
it, right?
Yes.
So this is the basic understanding. I just wanted to give you that derivation of stresses. Now after that, you will have to derive the strain, and you have to do the compatibility. Only thing is, I told you that we are not considering thickness in the thin shell or the plate element, but when it comes to a thick shell, we have to consider the thickness, and you have to model, like this is a slab. Okay, so you have to model the slab in layers if it is a thick element. So along the depth, it will be divided like this. So that way, you have to do the modeling, based on which the analysis results will come. So for thick shells, there will be some layers also. Along with the shear deformation will be distributed. These are the references that you should refer uh, if you have to be more confident in using the shear deformation theories, or the, at least for the first order as well. Hope my screen is visible to all. And this SI unit we have used. This is what you would also be using for doing your part. So most of you would be doing in the buildings. This is what is a normal thing. So let me take a portal frame in which 2 by 2 portal frame is there. And the height is not of that particular importance. So there is an option of flat slab with perimeter beams. I think all buildings with the core at the center are modeled with perimeter beams at the corners. Okay. So perimeter beam at the end of the building. So this is the mandatory requirement. This all would be following. And this is general flat slab design in which the column as well as the other means what say normal flat slab that we are doing like this. And flat slab with perimeter beam is the mandatory one. And again, there is a waffle slab can be used. Let me first define all the elements, define the material properties and the elements. It is already defined, so I'll not change it. So here you can see there is a layered option given. So if you go will by a layered option, you will go into thick shell. Now if you go to membrane, then membrane will be 456 2000. This is how you will design it, in which you don't have to modify any property because it will take only the actual forces and that we are not reducing. So let's say if it is a 150 slab, so that is one definition we'll give of the membrane. So right slab as a slab as a thin shell. Now the important part comes is this directions 1, 2, and 2, 2. Here you are not seeing anything called 3. Why that is there? My question is why you are not seeing any 3 direction in the except the shear. That also it is not in the principal direction. So can anybody tell why there is no third direction? So based on the understanding that we went through, some of the theory that I just just superficially, I could tell you. Okay. So based on that understanding, that is a very scratch level fundamental. Can you tell why third direction is not there? Then I can understand that you have grasped something that I told you. So anyone, because this is very crucial. So that's why I want to take you in depth into it. We can take any much of time as possible. Okay, so I'll just show you the difference also. So I could find one something on the internet, searching for that comparison. So this is that. So membrane element, the behavior is in plane forces only, in plane stiffness only. Okay. Now plate element out of plane bending plus in plane. Both is there. So in plane is there. Membrane action will be there in the plate element. But out of plane forces are also there. So out of plane bending plus in plane forces. Flexural stiffness plus negligible thickness. So thickness is very negligible in this particular case. So there are thin plates and thick plates. Types are there. There is membrane has no types. So in plane is there. Out of plane bending forces is there. So in plane forces, out of plane bending. So it is a combination of the two. Considering the flexural stiffness. So when you are taking the shell element, the flexural stiffness comes into picture. Otherwise, it does not come into picture. So if you want the slab as an element which has some stiffness out of plane, you have to model it as a shell element along with the shear consideration. So many times you will see that thin shells are modeled as plates because they have flexural stiffness, but their thickness is not considered. So it is a 2D element. Shell element on the same part is not a 2D element. It has some shear consideration into it. It is a 3D element, but it may be a thin or a thick. So shear stress will dominate or not dominate in the shell element, but it is a 3D element and plate is a 2D element. So what can be modeled like stair slab, precast slab, ramp, deck slab. So all these are applications of your membrane. And if it is a bridge deck, then you can model it as a plate or some type of flooring systems also you can do. Now, when it comes to aircraft fuselages, car bodies, building roofs, mostly the roof of the building, pressure vessel, pipe, all these are considered using the shells. So thin shells, negligible, thick shells, significant. So the shear deformations in thin shells is very negligible, but there thin plates it is mostly not considered. When it is a thick shell, the shear deformation is significant, and in the thick plates also it is significant. So you can see some relation between thin plates and thin shells. That's why when you are doing modeling in the StatPro, we are mostly taking it as a plate, whereas in the ETABS we are taking it as a thin shell. When you take a membrane, there is no shear deformation, and that's why it does not participate along out of plane bending. So what we were looking was M11, M12 in ETABS. So many would have searched on the CSI knowledge base. We should go there directly to understand it. So I hope now you are able to understand with the diagram that I had drawn for dx, dy, dz, and what they have drawn for axis 1, axis 2. Okay. So are you able to relate with it or not relate with it? That is my question. So anybody would like to speak on that? Are you able to relate it or not with the sketch I had made?
Sir, regarding this, if the global axis is considered, this is okay. But what if the local axis is considered? As every notations and signatures are changed.
No, whatever you are modeling, the element, right? Element is always in the local axis,
Uh,
right?
okay, sir.
Slab is oriented in x. So
Yes,
x
sir.
of the element will be x always. So that's why there is this angle theta is there. If it is having some angle with respect to your some system, that is particular column has its own xyz, and
Yes, sir.
full building has its own xyz. So building
Yes, sir.
xyz, column xyz, both are different. Same xyz of the slab and the building may be separate, but at element level, it is at member only. It is xyz of particular member. They may be with a global system or not, but your definition is in local system, which may be same as global system or may not be same as global system.
Yes.
Your definition always in the local system, x, y, z. So column x, column y, column z, x is longitudinal, z is major axis, y is minor axis. This is a local axis. For building, x, y, z is whatever you have modeled, considered based on that it will come. But for element, it is longitudinal, major and minor for the column. Same for the slab. You have to just follow what I told you before this. Just implement it here.
Okay. Yes,
Okay.
sir. Yes, sir.
So let us try to modeling concrete crack section properties for building analysis. So this was mentioned in 2017. Okay. So in ETAP, shell or area element has two types of stiffnesses. In plane stiffness. What is in plane? Now you know, like a membrane. This is a membrane action. It will transfer forces from one side to other side to the supporting member. Nothing out of plane. Are you clear with it? So shell or area element has two type of stiffnesses. In plane is given as a membrane. So when you are modeling it as a membrane, it will go only axial forces. Okay? And it will not have M11, M22, M12. So membrane will not have these M values. Membrane will have only the F values. I hope I am able to clear that very specifically.
Sir,
Now,
F12 is the shear force.
yeah. So that I will come to its particular notations. But
Yes.
only thing is membrane versus shell. I just want to give the bifurcation to you. Now, we'll go into the full forms of that F11, F12 later. So refer to the below figure which shows the direction of local axis. If you have read it clearly, you will know that this is the local axis only. This is not a global axis. So element wise, this is the local axis. You have to find the local axis of the particular uh, slab, and you have to assign the values that are particular to that directions. Don't assume it as a global direction, or don't confuse if you do the wrong orientation. If you give the wrong values in the wrong parameter, you will not get the result correctly. So you have to be very clear that these are the directions of the local axis and their corresponding stiffnesses you have to now model. Okay. So we are actually doing in plane stiffness parameter, out of plane stiffness parameter, in plane given by F11, which is direction 1. So how I had mentioned, that sigma x. Okay. So in that time, you had seen that there was some xy subscript was there. So force is in the one direction. Okay, this is the normal axis. First axis is your normal axis. So I'll go again to the PPT. So sigma x, here you see the normal axis. So tau xy, x is the normal axis, and z is the direction in which the force is applied. Same, you have to apply it here. One is the normal axis on which the stress is being applied, and one is the direction in which the force is there. So this will be my sigma x. Okay. Now again, this will be my sigma y. Okay. Am I clear? So normal is 2 and force in direction of. Now, as you had, again, I'll go to my PPT. I had told you that we are converting this three-dimensional 6x6 matrix to 2x2 matrix. So sigma x, sigma y, you got what? F11, F22. Now what you want is tau xy and tau yx. This is remaining in the matrix. The same you can see it here. F12 and F21 both are the same values. Okay, so this is the tangential stress of a 2x2 matrix that you use. This is sigma x, my sigma y, and this is my tau xy. Am I clear?
Yes, sir.
So these are the directions in which the stress in plane is applied. So in plane is x, in plane is y. So these are the forces, right? Am I clear? These are the forces. Now these are the moments. So for two things you have to apply. So here you can see whatever is in the single arrow is the force. Whatever you see in double arrow is a moment, right? So there are two types of moment. One is the bending moment and one is the twisting moment. So is twisting moment going to apply here or not? That we have to see, but bending moment is going to be applied. And there is no third direction, so twisting moment is not there. If third direction would have been there, then the twist in the system get generated. Now there is no twist. We are considering 2D element. We are using the Mendelian theory. Then there is no question of the third direction. So same, what I am doing the moment perpendicular, your normal direction is 1 and moment is about 1. Okay. Normal direction is 2 and moment is about 2. So moment is about 2. That means what? So F, let us first go with the forces. There is a axis 1 here. There is a axis 2 here. There are the coordinate system J1, J2, J3, J4. Cartesian coordinate or the coordinate points are given for the element. And there are two axes drawn. Now that some angle of theta, that is the normal stresses. These are the principal stresses. Now you know that F11, F22, two direction are there, and F12 are the tangential stresses that I had drawn tau xy. Same, they have drawn it here. So two are opposite, two are opposite. So tangential stresses, plane stress, plane strain theory that we are applying it here. So if you refer any book on applied mechanics, you will be able to get it. And advanced, solid mechanics, and there is applied solid mechanics or advanced solid mechanics. So you need to refer two books. One is solid mechanics, one is advanced solid mechanics. then you will reach to that derivation, strain, so you can compare with the software. Okay, so I hope this diagram and my diagram, what I had shown, is making some sense to you and giving some understanding that what you are actually providing to the software. So transverse shear not shown, positive transverse shear forces and stresses acting on positive faces point toward the viewer. So what you can see the dot are the transverse shear. So transverse shear, that means it will give out of plane bending action. This is in plane bending action, and transverse shear will give the out of plane bending action to us. So that can only come if you model it as a shell. If you model it as a membrane, it will not happen. So plate or shell, you have only two options. StatPro you model as plate, here you model as shell. Okay, so not membrane. So membrane will not have out of plane shear action. So I go to the moment side. Same is going to happen. Now you see normal direction is one. Okay, but force is acting in the second direction. How force is acting in the second direction? So axis 1 1. Mark on the screen. Yeah, now I can end. You are able to see my annotation, what I am drawing the arrow. Are you able to see the arrow?
It is
Hello?
showing access error.
Access. No, no. Can you see what I have drawn?
Yes, sir.
So you don't have to get the access, but you should be able to see it. Okay. So I think if this is clear to you, so what is this moment? Is this moment X
So
or
actually,
is
it is
this
showing.
moment?
We are not able to be visible it. Access error it is showing an anomalous users cannot annotate at this time, sir. We are not able to see the screen, sir. What is happening behind?
Can you see the M I have written?
No, sir.
No. Again, I'm trying. If you are able to see the arrow, red arrow, then let me know. Red arrow and M I have written. So if it is clear to you, let me know. Not clear to you, then I'll just make it on another page.
Yes, sir. It's visible, sir.
Visible, na? Okay, so annotation should be visible to all. So this is the moment MM I have marked on axis 1 and axis 2. So you tell me where is moment X and where is moment Y for this particular slab. So if I take 1 as X and axis 2 as Y, so where is moment X and where is moment Y? So this will be moment Y, right? And this will be moment X.
Sir, the page is visible, but what you are writing, only we are able to see the crosshair that the mouse pointer we are able to see, but what you are drawing, it is not visible.
So can you see my screen now?
Yes, sir.
Now I'll mark it here. So is it visible to you?
Yes,
Moment
sir.
Yes,
and
sir.
the
Yeah.
okay, okay. So I mark axis one as X and axis two as Y. So where is moment X and moment Y? Let me know if this is correct or not. Correct.
Sir, the opposite will be true. I think, sir, in the x direction there will be mx, and in the y direction it will be my.
Why?
Sir, because in the x direction, if we see, the bending will occur about the other two faces. But if we see the my, the bending will occur about the other two faces, other opposite two faces, sir.
So this moment that I am showing, right? This particular moment. This moment, what I have circled, will lead to moment between these 2 points, right? Will bend. Okay, this will bend like this. The slab will bend like this, right? In the out of plane, not in plan, out of plane. Am I right or not? So
Yes, sir.
so this is particular which direction the bending will happen. So bending will happen between these two parallel faces, right?
Yes.
When bending will happen between these two parallel faces, okay. So basically, these two red lines will bend down, and these two faces that are not lined but this tick mark is done will stay at its place. Okay. So two red lines will bend and two other black lines will be at its position. So what direction of bending it will? So red lines are going down. Okay. So it will go like this, right? and this point will be, let's say, J4, and this point will be J1. So between the two, the bending will happen. And if I model the axis here, then along the length is Y, right? Along the width is X, Z. So your moment has been applied about X, which has led to the deformation in the Y direction. Okay. So I think the marked dimension is correct as per me. Or if you have some more comments, you can correct me. Something I have wrongly marked here. So moment about X means what will happen that your what I have ticked, those points will bend and this will remain as it is. So it will be bending about the X direction. Bending in the X direction and moment about the Y direction. So is it correct or not correct? I just want to check from you. Yeah, so you need to be fast on that because very fundamental rule. Just if it is right or wrong, just let me know. Okay, let us keep it right now as it is, whatever I have marked. Okay. So what I am trying to tell you is M12, they have marked. So one is the normal force, normal surface where the force is acting, and is the direction in which the force is acting. Okay. And this will be M12 and this is again M12. This is M11 and this is M22. Okay. So now let us see the full form of all these moments. Then it will be clear to you. So flat plates and flat slab model as membrane. So what they have mentioned here, okay, whenever you are modeling as a membrane, modeled as a membrane, you have to give in-plane forces 0.25 as per ACI code. Okay. So for that they have given it here. Uh, the table we have to refer, but modeled as shell when it is a walls. So in plane, when you are giving a shear wall, you have to give in plane forces also. So in plane is F11, F22 for the shear walls which are uncracked, and walls that are cracked 0.35 or similar to walls uncracked with modifier of 0.35. Instead of 0.7, you have to give modifier of 0.35. Then, so this is the definition of the ACI code, not the Indian code, but logic remains the same. Now, in this particular beam, so 2 and 3 direction. This is the local axis 2, local axis 3. So local axis 1 is the longitudinal length of the beam, which we don't give. The bending stiffness is in the what we say the x and z direction. Okay, that's why 2 and 3 we are giving 0.35, not not the 1 is the longitudinal direction of the beam. Same 1 is the longitudinal direction of the column, so not given. So 2 and 3 is 0.7. That is the major axis, minor axis. 0.7 is the flexural stiffness for the beams and columns. For the shear wall, you have to give in plane stresses because we are not considering out of plane for the shear wall. But if you are considering out of plane for the shear wall, then you have to give for the moment as well. Now, when we are reaching at the membrane definition, so what it is saying that in plane forces to be given 0.25, not the moments, if it is a membrane. So flat plates and flat slabs are modeled as membrane as per ACI code. If it is modeled as shell, then you have to give F11, F22, F12, that is in plane. Out of plane, M11, M22, M12 as 0.25 for both cases. Okay. So the moments are out of plane, forces are in plane, both have to be given 0.25 as per ACI code. Okay, not we are not looking at Indian code definition. That's why I'm specifying it. You have to refer with respect to the Indian code, but the logic remains the same. So what we had seen in this previous case. Okay, so now I can go directly to the last point. That is the stiffness modifiers that model the out of plane stiffness of a shear wall and its cracking behavior. Let's say it is shear wall or any other thing. It remains M11 is bending about axis 1, bending about axis 2, twisting effect of the shell. So M12 is for twisting and two direction bending. That is critical to understand that M12 is twisting effect of the shell. This specific to wall, which we are not yet interested. We are interested in the floor. You don't look at internet like this, but you have to be very careful in what you are referring. So maybe in SAP 2000, if you search, it will be better. So it is giving the better options in SAP 2000 for the flows. So now you can see the same diagram that I had also modeled. Here also you can see that phase 1, phase 2, phase 3, positive phase, negative phase. That way it has been defined. But exact for the floor element, you are not able to see. Okay, but what understanding we have developed while going through that theory. Okay, same has to be applied. Now, Mr. Rabani, are you there?
Yes, sir.
So now is it clear your question that you had raised initially that what modifiers to put at what place?
Yes, sir.
So
Yes, sir.
are you able to hear me? Earpiece has Hello, are you able to hear me? Hello.
Yes, sir. Yes, sir.
Okay, okay, fine. So my target for today was to give an understanding of the modifiers. So F11 is in the in-plane direction X, F22 in-plane direction Y of the force, and this is the tangential stress. So this is for the membrane element, and when you are going with moment, you are going towards the shell element. Okay. Now the shear V13 and V23, where it is going to develop, like the force is acting in the one direction. The normal phase is one, but the force is generated in third direction. Fourth, this direction is two, but force direction is three. Okay, the shear values. When will this come into picture? Like we had seen in this also uh, that one, two, three directions are there. Internal forces and stresses. If we go into it, they have given the full form. It is easy. Otherwise, we have to search for it again. So this diagram is quite clear that M21 is equals to M12. These are the shear forces. M22 is the bending moment, and M11 is the bending moment, and M12 is the twisting moment. So these are both are the twisting moments. So all four directions twisting moment is there, and two directions you can see one positive, one negative, two opposite direction, two positive, two negative. So this is generating a couple. So top uh, direction and bottom direction are opposite, so they are generating a couple and generating a moment in the two direction. So your this is the bending moment. One also the couple is there generating the moment, and you can see two one and one two are the twisting moments. So this way it is represented on a 3D object, but we are doing a 2D in the plate or the thin shells. So this shear domination happens when you are doing with the foundations. Okay, so let us go to the shear forces also, which is represented by V. Hmm. So basic shell element forces and moments are identified as moment, force, and the shear values. Okay. Now you expect this fine, but they are not given the full form, so I cannot directly show you here. But whatever I will give, get it. I'll share with you in email also that how V23 is generated. You can see there is a force in direction 1, 2. Okay, and there is a force in direction 1, 2 in two opposite directions. So this generates a shear. Okay. Now you see F11 is the direction. So F12 is the shear. F11 in direction X. F11 in direction negative X. F22 in Y. F22 in negative Y. Then F12 and F22 are the shear forces along the perimeter. Now the third force has generated as V13. So why we are looking at V13, the third dimension has come because axis 1 and 2 are the plane direction. You can see dotted line, that is a plane direction, plane XY direction, and third axis is out of that XY plane. Okay. Now there is a shear generated along the third axis. That is represented as V13 due to the force in one direction. The shear stress is generated in the third direction. So direction is in the 3 z axis. Normal phase is 1. Now same for force generated in 2, that generated in 2 but developed in 3. Okay, so normal phase is 2 and force developed in the third direction. So that all will come in the equilibrium. So moment equilibrium, force equilibrium, and shear force also is there. So that all will be in the equilibrium. So based on the equilibrium diagram, you can see positive, negative signs here on the 3D object on which the forces are getting generated. So for the 3D element, this is the realistic description of the forces. We are eliminating V in many cases because that is not the dominant force. Bending and axial forces are that we are modeling, not in the shear direction V. So if we go again back to this particular same thing that we had seen, there is no description of V here. So what is the reason there is no description of V? So in the shell element in ETABS that you saw, it is not showing any V direction. And while in the other for SAP 2000 that we saw, it is showing in the shear in the V direction. You are getting what I'm trying to say. The difference between the two, why we are not adding shear V, any modifier for that. We are adding modifier only for the flexural stiffness. We are not adding modifier for the shear stiffness. Okay, so in which case the shear stiffness will come, that I can share with you later. But for these two values, you have to refer a different literature and different type of a problem, not in this particular case. So you will give 0.25, 0.25, 0.25 for membrane, 0.25, 0.25, 0.25 up till here if it is a shell. So any doubt is there how what we are doing? The results we can compare it in the second part. Okay. And for today's session, I had expected that at least I can give you the fundamental, what directions are there and what to expect. So I hope I have tried to meet up to the first level of expectation. The results we can compare and we can also do ourselves also. You can make a problem. We can see it next time. But I hope what I'm trying to convey is simple and clear to you for application purpose with good background. So Shahid, is it clear the questions?
Yes, sir. Yes, sir. Today it was great, sir. It is clear.
So can you speak a bit louder? I could not hear. Maybe my system.
Sir, today got the concept, basic concept, and it is clear, sir. The regarding the M11 and the shear force directions. Sir, that shear force, while in the shell element, the shear force is not dominating. But sir, you said that you will explain in which case we will consider that.
I'm not able to get you. Maybe some. I don't know the
The shear
reason.
force, the V13 in SAP in ETAPS, we are not getting the option of V13 and the other the shear force along the Z direction. But in SAP we are getting.
No, the shear option is there for all softwares. It is there, but in which case to use it?
Yes,
For
sir.
slabs, we are not using it. Maybe for foundations, we would need it, but for foundations, we are not doing any stiffness modifiers, right?
Uh, yes, yes, sir.
So that way, so for some other type of slab element in which the shear domination is there, you have to give the modifier for that.
Yes, sir, yes.
So thick shell, the shear will dominate. So when it becomes a thick shell, you have to give for shear as well. So in
Oh,
thin shell, it is not needed. You
sir, how
can
we will
make it
decide
as a
the
2D
values?
element.
Sir, how we will decide the values that how much we have to give that modifiers, like for the foundation or for the thick cells, if we need to design that. So,
Is it problem from my side? I'm not able to hear clearly or what?
sir, actually, sir, am I clear right now, sir?
Your volume is a bit low.
Okay, sir. Sir, what I am saying now, sir, for the like the shear forces along the Z directions, like for the foundation, we have to accommodate, or maybe in the thick shells, but there needs to be some values. So how can we get the values about that? How much, any range of the values that we can give, or any from any material where it is written or something like that, sir?
So IS code does not have any given V value. ACI code you can refer, it is given there.
Okay, sir.
Yeah.
ACI. Yes. Thank you, sir.
Okay, Rahul, any questions?
Uh, Sir, earlier, that length of the element will be the smaller and the smaller or will be the largest for specifying value of t. You said that it will be length of the element divided by 10. So in order to consider in the thick shell, we have to calculate first t value. T is our thickness of slab. If it is greater than the 1/10 of the length of the element, then we will consider in the thick shell, right, sir?
Yeah, yeah. That is the
Uh,
classification given.
Okay, but the length of element will be smaller or the largest, say for example, rectangle.
Longer
Okay,
dimension.
okay, okay.
Like it is a one-way slab which is 1 meter by let's say 8 meter.
Okay,
Okay. So it may be 1 meter by 7 meter, like precast slabs are also there. So its bending is in the longer direction, right?
okay,
So it will act as a thick or not will depend upon the larger dimension or a global its deformation with respect to thickness.
uh, okay, okay. And
Yeah.
that V13 and V23 will come into flat slab as well because in flat slab shear is governing. So,
No, we are modeling it as a 2D element, not as a thick slab, thick shell. So thick shell is related to the thickness. Flat slab also are actually having lesser thickness. Now, if your thickness is of such that amount that your longer dimension versus thickness is having a ratio of more than 10, then you can take it as a thick shell.
okay, okay,
Sir, regarding the IS code, design of the slabs as per the IS code, sir, you said like we have to design like like we have in IS code we design like a membrane, but
Yeah,
in the real action, sir, there is a bending.
yeah.
So, sir, is it safe to design from the IS code? Because if you will design some slab specifying that we are designing from the IS code, it is acceptable.
The design of slab as per the IS code only you have to do, right? Compliance is as per IS 456, not as per IS 1893. Now you are doing the crack modeling
Yes, sir.
in the slab also to reduce the reinforcement in beams. That is the main reason people use the modifiers in the
Mm.
slab so that we can use the stiffness of the slab and reduce the moment in the beams. But as per the IS 456, if you go, then there is no Indian standard saying that uh, you design in the software using FEA, but alternate solutions have been prescribed by the code. Okay, so there is one what we can say minimum safety requirement, or
Yeah.
whenever you are modeling, if you are modeling it wrong,
Mm.
okay, then it will be a serious problem. So
Yes,
that's
sir.
why what code says that this is the membrane element. If you take it, then it will give higher reinforcement in the beams, but your slab will be okay.
Sir, but
Yeah.
modeling the membrane, sir, we are accounting for the bending. So we are not accounting for the bending now.
So what will happen? See, the drawback of modeling it as a membrane is that actual shear stresses that are generated during the backstay effect also and in the floor system will not get modeled. So you will not design for it. Okay. So that is the drawback if you don't model it as a thin shell. So in the cases where the geometry is not simple or the building is a high rise and podium is also there, transfer of forces taking place from one floor to the other floor. In that particular cases, you should model as a thin shell and finite element, and you will get real benefit for the slab. And for the overall beam design, if you model it as a shell, then beam reinforcement will also reduce. You will take benefit of stiffness of the slab. But there is no yet a guideline in India that asks you to do that. But logic and the software, logic and the theory says that you should model it as a shell in the software. So
Mm.
where it is
Okay.
mandatory to model, you should model.
Yes.
So
Thank you, sir.
superseding also requires some logic, understanding, and application
Mm.
of it should be proper, not wrong.
Okay. Thank you, sir.
Yeah. So, Mr. Joshi, are you there? Okay, so we can end the session for today, the part 1. I'll let you know for the part 2 over email. Yeah. A recorded session will reach you in maybe two days. By that time, you can start searching for the shear deformation theory at least and get more understanding of it till we reach. And you can also evaluate problems in the software safe and the ETABS so that we can also discuss it next time. Thank you
Thank you. Thank
Thank
and
you.
happy Diwali once. Yeah, bye.
Happy Diwali to
Same
you,
to
sir,
you.
as well.
Thank you.